Hello, this is Ira again. Today we're gonna go over sensors and detectors. We're gonna review knowledge 5 this time. And in knowledge 5, we're gonna see some of flow detectors, divergent nozzle, the Venturi, Orifice. We're gonna take a look at the manometer, and we're gonna take a look at Bernoulli's and how to apply that information to obtain the pressure of cooling water system. Okay, let's dive into it. So we have flow detectors is the first thing that we're gonna take a look in here, and it's the flow detectors help us measure flow rate passing through a Venturi, and that's basically the only thing that we need to know for this. It measures the flow rate. That's what it does, and we're gonna use this relationship. The flow rate is going to be proportional to the differential pressure of the Venturi. And we have a Venturi here, and we will explain that in a little bit. But next, we're going to have a divergent nozzle. And for a divergent nozzle, so we're going to have this Venturi, or we're going to have this convergent divergent nozzle. And this part of the Venturi is the convergent part. This part is the divergent part. And when we put them together, converger divergent part, we are going to have also what we call a Venturi. The thing that we need to know that we will see in the GFEs, and it's important, is that the outlet pressure on a divergent is going to be higher than the inlet pressure. And that's it. Also, we're going to have some orifices, right? So in any flow system where we're trying to measure the pressure, we're going to have some orifices where we're going to put all the meters and whatnot. So this orifice is going to cause a largest unrecoverable head loss. And for GFEs, that's all that we know or that we need to know. So let's go back and take a look. Okay, so the divergent nozzle. Let's review this because I think it's important. So divergent nozzle, what is that? So a nozzle is something that generates thrust. So the objective of a nozzle is to increase its kinetic energy, increase the kinetic energy of a flowing medium at the expense of its pressure and internal energy. So that's what it's trying to do. So nozzle can be described as we already said, convergent and divergent. So a convergent nozzle is gonna give us a narrowing down. It's gonna start narrowing down from a wide diameter to a small diameter. And that's gonna be the direction of the flow. And a divergent nozzle is gonna be expanding from a smaller diameter to a larger diameter. A nozzle with a convergent section followed by a divergent section is often called convergent divergent nozzle, or we can also call it a Venturi. So again, so we mentioned that the nozzles generate thrust, but what is that? So thrust is a reaction force described quantitatively by Newton's third law. So when a system expels or accelerates mass in one direction, the accelerated mass will cause a force of equal magnitude but opposite direction. And this is important. It's going to cause a force of equal magnitude but opposite direction to be applied to that system. So the force applied on a surface in a direction perpendicular or normal to the surface is also called thrust. And an example of that we can see in an aircraft. So the thrust is the force that moves the aircraft through the air. And that's all we need to know. So here for GFEs, what we actually need to know is that here we're gonna have the area of high pressure. In the middle area on the choke is like where we have like the smallest area. We're gonna have the lowest pressure. But if we go here to this detector in this area D, the pressure goes up, but not as much as initially it was, right? So it doesn't go all the way up. Contrary to velocity, velocity goes back to its original velocity. So here we have high velocity, lowest velocity, and again high velocity. So just remember, this is area of high pressure and low pressure. And this is going to be high pressure, but not as high as the original pressure. And for GFEs, that's basically all that we need to know on this part, on this section 5. Now, we have a manometer. So a manometer is going to be a device that measures pressure. And a common simple manometer is going to be U-shaped. It's just basically like you have something on a pipe here. And this thing is just going to try to measure. Right, so let's say this is a manometer, so we have some fluid in here. So we have the fluid moving in this direction or moving in that direction. We will see the pins, right? And I will go over that one later. In this case, it's going that direction. So this manometer, it's a U-shaped tube of glass, and it's gonna be filled with some liquid, right? And we're gonna try to measure the differential pressure. So for GFEs, we're gonna just do some ratios here, because it's gonna ask us different questions. It's gonna ask us about the flow rate on the manometer, the final flow rate, or the final differential pressure on the manometer, and we're gonna use the same formula we've been using. Is the flow, it's proportional to the square root of the differential pressure, and that's the formula that we're gonna use in here. So then, lastly, we're gonna have to go over Bernoulli's equation, and in the example I explained a little bit more about that. But Bernoulli's equation basically describes a relationship between the velocity, density, and pressure of a flow. And it's basically a conservation of energy law for a flowing fluid. So this is a derivation for Bernoulli's equation that we are giving on GFEs. So this is the derivation that I use, and I like this derivation because to me it's easier to remember than trying to derive the formula from Bernoulli's from the Bernoulli's equation. So I like to use this one. So for this one, we're gonna be given an initial pressure. We're gonna be given the temperature from the fluid, and from there we can get the specific volume of the fluid. We're gonna be given initial and final velocity. And here we are just on conversion factors, right? So those are just conversion factors. And since this part is gonna be the same, so it helps me remember, this just helps me remember the formula. So when I get the answer of this, I will get it in pound force over inch square, and that is PSIA. You just need to be careful. Sometimes we need to convert from PSIA to PSIG, right? So we need to make sure that we know how to convert that. And now let's go over and take a look at some of the problems then. Here we have some of the problems. So let's start with this one. This is gonna be problem P308 or the question ID P308. This is what we have. A cooling water system is operating at a steady state condition, indicating 900 gallons per minute with a 60 psid pressure, differential pressure across the flow transmitter Venturi. If the cooling water flow rate is increased to 1800 GPM, the differential pressure across the flow transmitter Venturi will be what? So in this one, we just need to use the relationship, right? We use our relationship. Volumetric flow rate is proportional to the differential pressure of the Venturi. So this is the relationship that we're using. So we need to derive a formula because we need to get the ratios basically. So here, what we do is I'm gonna make this bigger. So we got my flow initial over my flow final and my differential pressure initial over my differential pressure final. I rearrange and I'm gonna end up with this formula because it's asking me about the differential pressure across the flow transmitter, right? So I need to know the differential pressure final. That's what I need to get from here. So if I try to get that, I just plug in the numbers in here. So dP final is gonna be equal to my 60 PSID, and then I have my 900 GPM over my 1800 GPM, that's square. So I think the answer is going to be 240, right? This ends up being 4. So my answer is going to be 240 PSID. And that's how we solve this type of problems. And we're going to have more in the question bank that we can practice with. So now let's go over and take a look at another problem. So, and this is another problem. It's going to be similar. We're going to use a similar relationship. In this case, we're going to use the mass flow rate of the steam be proportional to the square root of the differential pressure. So let's take a look at this question ID K1.07. The question states, a differential pressure detector is being used with a Venturi to measure main steam flow rate. With a steam flow rate of 5 times 10 to the 6 pound mass per hour. So that's something important. So that's my first value, right? And it's telling me that the measured dP is 40 PSID. Those are my initial values. If the steam flow changes such that the current dP is 30 PSID, so now my new dP is going to be 30 PSID. What is the approximate current flow rate? So I need to get a new flow rate. So we use kind of like the same relationship, right? And we just need to rearrange the formula and solve. So in this case, we're solving for the flow rate. We're not solving for the differential pressure. So now we have the mass flow rate final is going to be equal to my 5 times 10 to the 6 pound mass per hour. That is going to be 30 PSID over the square root of 40 PSID. And I will get my final, I plug in everything in the calculator. This is my answer. It's going to be 4.33 times 10 to the 6 pound mass per hour. And yes, I have an answer similar to that one. So it's this one. And this is how we solve this one. I think on this one, there's only like 2 problems like that. But we know how to solve them. So we got that information there. Let's take a look at another problem. Let's see. As you can see, there are many. But with the information that I gave you previously, you can solve for any of this. No problem. See, as you can see, this other one is going to be similar. You are giving the volume. So you need to get the, you need to get the differential pressure final on this one. That's what he's asking for. We know how to solve that. We have the formula. So, okay, now let's take a look at this one. This one is a little different. This one is the question ID K1.05. We have a differential pressure detector that is being used with an orifice plate to measure water flow rate through a pipe. When the flow detector was calibrated, the following parameters were observed. So it gives you like a lot of information, but you just need to focus on getting the information that it's important that you're gonna use with the formulas and all the information that I gave you previously. So if they're giving you this, that means that you can calculate the differential pressure. So then you go and calculate the differential pressure. So you got that, okay? You got your differential pressure initial. Now, they're telling you the actual flow rate and the indicated flow rate. Remember what the formula says. So volumetric flow rate indicated is proportional to the square root of the differential pressure of the Venturi. So we just need to remember that this is an X parameter because we don't know if it's this one or this one, but yeah, no, I mean the formula is saying that the volumetric flow rate indicated is going to be proportional to the differential pressure. So this is the value that we need to use. So let's continue with the question. Significant erosion of the orifice has occurred since the calibration, such that actual flow rate through the orifice has increased to 120 GPM, while the upstream and downstream pressures have changed to 110 and 106. So if you read that, you will get a little confused because you might think, okay, I'm giving the final volumetric and then I'm giving this pressure change, but this is not the indicated. This is the actual flow rate of the orifice has increased. This is the actual flow rate. So we need to calculate the indicated flow rate, right? And we use the same formula to calculate it. So we can use the ratio. So we already rearrange our formula. So we get this. We get to use this formula, which is the volumetric flow rate final in here because we already calculated the differential pressures. So since we already have those differential pressures, we just need to plug in job. So we're gonna have, and I think it's just like being careful about the wording because here we're giving extra information that we might not need. So we're giving this one, we're giving this one. So we need to make sure that so this one says actual. So I don't need the actual, right? We just need to be careful with that. So and this one is, we plug it in the calculator and we get 66.67 GPM. So we can say that we get about 67 GPM, and that is the right answer. And we're gonna get similar, so as you can see, this one is very similar, so we know how to solve this one. We need to make sure that we select the indicated flow rate, right? Because this is the actual flow rate that is giving us, so we don't want that. Actual flow rate, we don't need to use that one, so we don't use this one. And okay, so we have this one. This is the last one that we will review, and this one is related to Bernoulli's. And in this one, I think we have another one down here probably. So it's here is this one. This is the one that I want to explain because here we take a look at Bernoulli's equation in this with this example. So this question ID is going to be question P4804. So the question states, a cooling water system uses a horizontal Venturi with a differential pressure flow detector to provide flow rate indication. Water enters and leaves the Venturi at 70 degrees. So this is going to be important. This temperature of the flow of the water. It is giving us the pressure initial, and it's giving us the initial velocity, right? So that's something that we're gonna use to solve this problem. What's next? So the water velocity at the throat of the Venturi is gonna be 50 seconds, 50 feet per second. So assume that the water is incompressible and the Venturi experiences no recoverable head loss. What do we need to do? We need to calculate the approximate pressure of the water at the throat of the Venturi. And so we are giving on the question banks or we are giving on the exam, we're giving this formula, we're giving this, the Bernoulli equation in here. That's what we're giving. So, since this is what we're giving, we need to make sure that we know how to use it. So what does each part mean? So this part of the equation is talking about the elevation. This other part of the equation is talking about the velocity. This other is talking about pressure, kinetic energy, and work. But let's remember, in this Venturi, we are not using the elevation. We are not using the kinetic energy and the work. So these ones are gonna go to zero. So we are gonna end up with this. This is what we're gonna need, right? So we need to use this. And from here, we can rearrange and get this formula. But as I mentioned before, I just memorize this formula. For me, it's easy because it's plug and check. Two things that we need to remember. We need to remember to convert from PSIA to PSIG. Here the answer is PSIG. We also need to convert from feet squared to inches. So we need to make sure that we have that conversion factor integrated in there, right? Because my answer is gonna be pound force over inch squared. So I need to make sure that I get that, right? Okay, so how will I solve this? First thing that I'm giving is the temperature of the water entering in the Venturi. So if I look at my steam table, right? If I use the specific volume of the water, right? The specific volume of the water at 70 degrees, and if I go to my steam table, I know that I will get my specific volume to be 0.01605 feet cubed over pound mass. So that's gonna be the number that I need. The rest of the numbers, I already have them, right? I'm giving here the 50. This one is gonna be my 50 feet per second. This one is going to be my 24. And this one is my 100, right? And this is the specific volume of the water at 70. So I already have everything I need. So you can see it's like way easier because now if I plug in all the numbers, I will go and get directly my pressure, right? So let's plug in the numbers. So I know it's 100 times 144, and I know this is PSIG. Yes, I know I shouldn't do that, but I'm a little lazy, and I don't want to confuse anybody more because I already have the values of here, and I know that my answer in here is gonna be 4 over inch squared anyway. So I already set it up for that. So this one will be 50 squared minus 24 squared over 64.4 over, and it's going to be the same as this one, 144 times 0.01605. Okay, so if I put that into my calculator, I'm going to get 102 pound-force over inch square. I just need to remember to convert to PSIG. So I just, for GFEs purpose, so 102 minus 15. So let's check how much is 102 minus 15 is going to be about 87 PSIG, right? Because this one I'm getting it in PSIA. So I just subtract 15 to get it into PSIG. And I have that in my answer, actually. So that's going to be right here. And that's all that I have for this section of the GFEs. Thank you.